Hello, everybody. Again, this is a continuation on Chapter 8. Let's go over the practice problem 8.6. We need to find the current I0 through the 7 ohm resistor using the source transformation. Now, again, so this is a current source. So since we are looking for the current I0 through the 7 ohm resistor, so we need just to somehow organize this current source into, put the current source to the left. Again, we could swap. And then since the 1 ohm and 4 ohm are in series, so this would be 5 ohms. And this is 3 amps. And then this is the 7 ohm resistor, I0. Again, as I mentioned earlier in the previous video, that we don't touch the element that we are looking to find the parameters through it. In this case, we're looking for I0. So the 7 ohm resistor we do not combine with any other element. And then we have the 5 ohm resistor, 5 volt source, as I mentioned also, that we need to move this voltage source down here, or in other words, we need to convert the 5 volt into a source current. And in order to do that, I need to convert the current source, which is a 3 and 6 are combined as one resistor, into a voltage source, and then convert this back to current source. So let's do this step here. We have the resistor combined of the 6 and 3 divided by 9, and we have 5 amps. So what I did here, combine the 3 and the 6 as one resistor, and then I will convert or transfer this current source into a voltage source, and then I combine the 2 voltage sources into one, and then convert it back into a current source. So at the end, I will have a parallel branches all together. Now, why I'm doing that? Because I'm looking for the current in a parallel branch or a vertical branch. Okay, so I leave this one here because that's what I'm looking for. So let's start with this one. So this one will be 2 ohms. 6 times 3 over 9, 18 over 9 is 2. And then we convert the 2 voltage source, current source to a voltage source. So 5 times 2 is 10. And then we have a resistor 2. And then we have the voltage source 5 volt. And then we have the 7 and the 5 and the current source 3. Okay, so 5 ohms. This is I0. 7 ohms. Again, do not touch, do not combine, do not move anywhere. So again, this is just a plus sign here. So now we have these 2 voltages, the 10 volt and the 5 volt, that will be added because they are connected in series. So minus 10 volt and minus 5 volt, both of them will be 15. So we have 15 volt. Then we have resistance 2. Then we keep, the rest of the circuit as before. Here's the 3 amps, here's the 5, here is the I0, and here's the 7 ohm. Now the last step is to make source transformation to the voltage source into current source, and then we combine the current sources and we combine the resistors in parallel, except the 7 ohm resistor. Okay, so let's redraw the circuit here. We draw the current source again, which is 15 divided by 2, 7.5. Okay. And then we have the 2 ohm resistor and the 7 and the 3 and the 5. So this is the 5 current source, sorry, the 3 amps, and the 5 ohms, and the 7 ohms, and the I0 and the 2. Okay, now we have the current sources. They are in the same direction, so they will be added. So this will be 7.5 plus 8 plus 3 will be 10.5. Then we combine the 2 and the 5, and we keep the 7, I0 goes through it, and 2 and the 5, so 2 times 5 is 10 over 7. Okay. And then we do the current division to find I0. Okay, so I0 will be 10.5 multiplied by 10 over 7 divided by 10 over 7 plus 7. Okay, so I hope the answer will be 1.78. Okay, so you can check this answer by using your calculator. Okay, so okay, now we move on to section 8.5, Thevenin theorem. And many circuits, one element will be variable. An example of this is main power. Many different applications may be plugged into the outlet, each presenting a different resistance. This variable element is called the load. Ordinarily, one would have to analyze the circuit for each change in the load. So what is the meaning of this? Why we do use Thevenin theorem? As it was stated, sometimes you need to plug different loads to the plug, to the outlet in our homes. So sometimes we plug a refrigerator, sometimes we plug a dryer, sometimes we plug a washer or dishwasher, and so on. So instead of analyzing the circuit to a different value of loads, every time we change the load, we need to analyze the circuit to find how much current flowing in that load. And the meaning of the load means that everything connected to the plug is called a load. Okay, if you plug a light, that light is called a load. It has a resistance. If we plug a toaster, that toaster we call the load, and it has a resistance. If we plug a TV, radio, Xbox, whatever we plug into the outlet, we call this as a load. So why Thevenin it's useful in this type of situation when we have a different loads applied to the source. Okay, and we'll see how we could use that one. So if we use a Thevenin one time, we don't need to analyze the circuit every time we change the load. And this is the beauty and the benefit of using Thevenin theorem. Thevenin theorem states that a linear two-terminal circuit may be replaced with a voltage source and a resistance. So at the end, no matter how large or how big the circuit is, if you have like 3, 4, 2 current or mixed of current sources, voltage sources, resistors 1, 2, 3, 4, 5, we can reduce all these elements into two elements, a voltage source and a resistance. So this is what is the Thevenin theorem is about. Complicated circuit, too many resistors, too many sources, we reduce all of these into a voltage source and resistor. The voltage source value is equal to the open circuit voltage at the terminal. So when we do the analysis, we take out the load, we remove the load as is stated here in this, here, this is our load. And again, this could be anything. Could be a resistor, could be a lamp, could be uh, a fan, could be a motor, could be a refrigerator, and so on. So in order, and this is our circuit. This could be two voltages, consists of two voltages, one or two plus another current sources, 5, 6 resistors. So we replace all this box, whatever inside in that box, into two elements. A voltage source, we call it VTH or VOC, V open circuit. Open circuit means we remove the load. And then whatever the value of the resistance determined by looking across the terminal A and B, the two terminals A and B, that's called RTH or R Thevenin. So we have the voltage source value is equal to the open circuit voltage at the terminals. Then the resistance is equal to the resistance measured at the terminals when the independent sources are turned off. So whatever inside this box, if there's any voltages, any current sources, those will be turned off, will be removed, and then determine the resistors locking between these two terminals across the load. So, and we'll see some examples to clarify and explain this theorem. There are two cases to consider when finding the equivalent resistance. Case one, if there are no dependent source, then the resistance may be found by simply turning off all the resistors. So if we have all the sources in the circuit are independent, then it's very simple to turn off those sources, take them away, replace them voltage source with a short circuit, current sources with an open circuit, and find the Thevenin resistor equivalent. If this is the case one, case two, if there are dependent sources, we still turn off all the independent sources, but we have to keep the dependent sources. Now apply a voltage V0 or current I0 to the terminal and determine the current I0 volt. So in this case, in order to find the R Thevenin, we have to apply a voltage, either a voltage source, small voltage source, any value, 1 volt, 2 volt, 3 volt, and then find the current I0, and then using the Ohm's law to find RTH. Or we could apply the I0. Again, these two terminals here, this is after we remove the load. So these two terminals, so this is just, it's not something that we have to do it. It's just a theory that we need to implement or apply any value of V0 or any value of I0. So either way, okay, either this step we use the V0 or we use the I0 in order to determine uh, the R Thevenin. Now again, we are going only focus on case one where there are no dependent source. Okay, Thevenin theorem is very powerful in circuit analysis. It allows one to simplify a circuit. A large circuit may be replaced by a single independent voltage source and a single resistor. So this is the beauty of the Thevenin. Just complicated circuit, large circuit, we can replace by two elements. Voltage source, independent voltage source in series with a single resistor. That voltage we call VTH or VThevenin or V open circuit, and the resistor we call it RTH or R Thevenin. The equivalent circuit behaves externally exactly the same as the original circuit. So even though that we simplify and we reduce the original circuit, but the new circuit or the Thevenin equivalent circuit, it will behave the same way as the original circuit. Okay, here's the example 8.8. Determine the Thevenin equivalent for the circuit to the left of the terminal AB. Okay, so what we need to do now here, we need to reduce the whole circuit here into actually not including the R. So in this case, R is our load. Okay, any element at the right hand side of terminal A and B, we call it the load. So in this case, we call it R. Okay, so what we need to do is to replace all the elements on the left side of terminal A and B into one voltage source we call VTH and a resistor in series with it. See here AB. So anything to the left of AB will be replaced by RTH and VTH. And then if we were asked to find what is the voltage across R if R is given, or what is the current through the R, and if R is given, then we just place the R here, whatever the value is, and then we find I, or the voltage across the R. So it's very simple, nice and easy steps to do in order to determine the equivalent, Thevenin equivalent circuit. Okay, so what we do here, so again, let's redraw the Thevenin equivalent circuit. Here's AB, here's RTH, and here's VTH. Okay, in order to find RTH and VTH, the first step we need to do, we need to remove R, or the load, if it exists. If R is not there, then that's fine. That's what we need. That's the first thing. You have to remove the load. You have to remove whatever we call it, R or RL. And then second step, to find RTH. To find RTH, so step 2, find RTH. To do that, we need to remove all the supply voltages or the current sources and replace the voltages or the independent, that has to be independent, have to be independent sources, current voltage sources or current sources. You have to be remove them and replace the voltage source, its terminal, by a short, and replace the current source, its terminal, by open circuit. So since we have 10 volt here, so we remove the 10 and then we replace. So again, we already removed the step number 1, we remove the R, and then we remove the voltage 10 volt and replaced by short circuit. And then we determine RTH looking between the two terminals of the load. Okay, we don't find the RTH from this side, for example, or from this side. We have to find it from where the two terminals are connected. Okay, so this is a very simple circuit. So again, always we start from the opposite end of where we are determining RTH. We determine RTH from this side, we have to start from here. Do not combine the 28 ohms with the 28 ohms. Okay, we have to start from the far end left. So again, the 20 and the so RTH will be 30 times 20 in parallel plus the 28. So this will be 40 ohm. Okay, so this will be step number 2 to find RTH. So almost we are on halfway to find the equivalent circuit, definite equivalent for the circuit. Okay, now step number 2 is to find VTH. Now to find VTH after we remove R, so we have to go back to the original circuit and remove, again, as I said, step number 1, remove RTH. Now, with the existence of all voltages exist in the circuit or current sources, whatever are exist, they have to be there. The 20, and this is 28, all ohms here. So we need to find the voltage here. So they call it, usually they call it VTH or VOC, V open circuit, because we open the circuit. Now, as we know that since there's no current to flow here, because this is an open, because that one, the R was removed, so there is no current flow, so there's no voltage drop. So all the voltage here is the same as the voltage here, because no voltage drop here. So this we can remove, we can ignore the 28 and we put the VTH down here. Okay. So again, very simple circuit, two resistors in series with a voltage source. We could determine VTH applying the what? The voltage divider. The voltage divider said that we need to find the I goes through this loop, and then I multiply by 20 to get VTH. So we have I is equal to 10 over 50. Okay, this is the total resistor to 50. Then multiply by 20. Okay, so again, voltage divider applying Ohm's law twice in one step. So 10 over 50 is I, and then I times 20 is another application of Ohm's law. So whatever, so that one will be, 1 will be 40 volt. Okay, so this is basically the steps of how to define, how to find the, this would be 4 volt. Okay. Okay, so the final answer to this problem is just to draw the equivalent circuit. Again, you could draw a circle, the plus or minus, or batteries. So that would be our VTH equal to 4 volt, and the resistance 40 ohm is RTH, and then we complete. So this circuit here is the same as the original circuit. Okay? So again, if we have R is equal, for example, let's say one ohm, then we can find I. So I would be VTH over RTH plus R. VTH is 4 and RTH is 40 plus 1, and so on. So we can change the value of the R without changing the original circuit. So this is the beauty of using Thevenin. You don't need to analyze the original circuit when you change R. So if we change R to 2 without using Thevenin, and we go to the original circuit here, then we have to analyze the whole circuit with the value of R is equal to. And then if we change R to 3 or 4 or 5, then we have to do the same many steps to analyze the circuit with the different value of R. But having the Thevenin, there is no need to analyze to include all of this in order to analyze the circuit when R is 3 or R is 2 or R is 4 or any other value. But what we need to do, find RTH will be constant all the time because those values are fixed. The only value is changing is the value of the load. Okay, so let's move to the next. Okay, here's another it's a practice example problem. Again, this is our load. So we remove the R, we find VTH, it's 8. VTH here, this is 12, this is 4 ohms, 8 volts. So again, VTH will be equal to 8 over 4 plus 12 multiplied by 12. Again, it doesn't matter whether you find VTH first or you find RTH second or third. Now, to find RTH, we have to remove the 8 volt and replace with, again, the R has to be removed from the beginning, even before we find VTH or RTH. So here's the 12. Here's the two terminals, A, B. Okay, R is removed. This is where we determine RTH. Then we have the R for ohms here and the 12. So RTH will be 4 multiplied by 12 over 16 will be 3 ohms. Okay, again, this will be 6 volt. Very simple, straightforward, but it's very powerful tool or theorem to use when we analyze different size of flows. Okay, again, here's the another example. Now, if you notice here that here's RL, okay, the RL is the resistance of the load. And what is a load? It's any electrical device connected to the power supply. Anything, any electrical device, heater, light bulb, refrigerator, as I mentioned earlier. Okay, so here in this case, we have a voltage source and a current source. So when we determine R Thevenin, we must remove both of them, but we have to short circuit the two terminals of the voltage and open circuit the two terminals of the current source. So to do that, first we need to remove RL, and then we need to find RTH. So again, here's AB. I have to remove the RL, and here's the one. Here's the, I'm going just to put two points here, two dots, to indicate this is the place of the current source, but it's an open. And then we have the 12, and we have the 4. Okay, the two terminals of the voltage source will be, again, the 32 will be removed and replaced by the short. Okay, so you could put, the short here if you want to indicate the location of the position of the 32 volt. Now, here's 4. Again, looking from here, again, this is an open. So again, all will start from the far end. So RTH will be equal to 4 in parallel with the 12 plus 1, and this would be 4 ohms. Okay, so that's step number 1. Step number 2, we need to find VTH. Finding VTH, we might need to use the other techniques that we used before. So we might need to use Ohm's law and nodal analysis or mesh analysis or source transformation. So that's why the previous chapters are very important to understand and to review. If you need to go back to them, please do so and review them again, because, you know, as we notice here, that we are just applying what we have already learned and studied in the previous chapters. Okay, so again, removing this one, we have now, so again, because this is an open circuit, so there's no current to flow. So the 1 ohm resistor has no effect on the VTH. So the VTH also could be put down here, okay, across the 2 ohm. Now again, we could use the mesh analysis as the book used. So let's try this here. So we need to find VTH here, okay? So VTH again here is the same as the voltage here, okay? Because these two elements are in parallel. So this one has no effect, no voltage drop. So the voltage here is the same as the voltage here, is the same as the voltage here. But it's not the same as the voltage here. Why? Because we have the 4 ohm resistor. So this node here, this become like one node, because again, the 1 ohm resistor has no effect. But if it has effect, you cannot call this the whole node. Okay. Yeah, this is one node, but this will be a different node if it's not an open circuit. Okay, so let's apply KVL around loop number 1. So it will be minus 32 plus now I1 will be 16 I1. Then minus I2 is a negative 12 I2 is equal to 0. Or 16 I1 minus 12 I2 equal to 32. Now we divide by 4. So that will be 4 I1 minus 3I2 equal to, so 32 over 4 is equal to 8. So just simplify so divide every term by. So this is the fundamental of an equation. If you divide one term by a number, you have to divide all other terms by the same number. Okay, so this is equation number 1. Now loop number 2 is so easy. So I2 is equal to negative 2. Okay. Now we need to find, I1 and I2 in order to find VTH. So again, VTH, let's put down here, VTH is equal to I1 minus I2 multiplied by 12. Okay. So we have to find the current here in the branch of the 12 ohm resistor, which is I1 minus I2. Why we said VTH is equal I1 minus I2, not I2 minus I1, because VTH, the plus here is the minus here, and the current flowing from this direction, that means the plus up and the negative down, so it has to be I1 minus I2. If VTH is a plus here and minus here, it will be I2 minus I1. So we just keep it like this. Okay. So now again we have I2. We need to find I1. So we can plug I2 here. So we get to find I1 will be minus 3 minus 2 equal to 8. So that will be 6. Oh, sorry, this will be plus. So for I1 plus minus I3. Yeah, there's no need for the plus here. There's no need for the plus. So it will be 4 I1 minus 3, and then multiply by I2. I2 is minus 2. So it will be 4 I1 plus 6 equal 8. Okay, so 4 I1 plus 6 equal 8. That leads to 4 I1 equal to 2. I1 equal to 0.5 amps. Okay, so then I1 minus I2, so will be 0.5 minus minus. Remember that is a minus, and we have a minus 2. Okay, multiplied by 12. So this will be 1.5 or 3 over 2. It's a plus here because so 2.5 multiplied by 12. So let's see what the answer of the book. Okay, so again, this will be 30 volt. Okay, so so that's how we determine the VTH, and after we do that, then we can build a circuit, the Thevenin equivalent circuit, and connect the R load or RL to that circuit, and then we have a complete circuit. Now let's see what else we can find. Okay, it asks us here, then find the current through RL. So here's the current, we need to find RL6, and then 16 and 36. So we could see here that using one time to find the Thevenin equivalent circuit, and then we can plug for RL equals 6, and then find the current through that load, and then replace it with 16 ohm, and then replace it with the 36 to find the current in the other two resistors. Now, if we use the other techniques like mesh analysis or nodal analysis or source transformation without using the definite, then we have to analyze the whole circuit at 3 times, when RL is equal to 6, and then when RL is equal to 16, and when RL equal to 36, in order to find the current that goes through this R load. So that's why the RTVN is very practical and easy and fast to use in this type of application. So again, let's go and build a circuit for VTH. So I said VTH is 30, and what is the? Let's go back to RTH. RTH is 4. Okay, here's 4 ohms, and then we put RL. So let's put it first. First question, we need to find RL, IL when RL is equal to 6. So 6 ohms, I need to find IL here, whatever you call it, IL or I. So again, using Ohm's law, so IL equal to 30 over 12. And then when we put RL is equal to 16 ohms, then new IL will be 30 over 4 plus 16, so it will be 30 over 20 amps. And then same thing when RL is equal 36, so IL at 36 ohms will be 30 over 4 plus 36. So as we notice here, that we only change the value of the RL in order to determine the load current. If we ask to find the voltage here across RL, then whatever 6 times IL, or then 16 times the new IL, and so on. Okay, so let's move on to, another example here. We need to find, using the Thevenin theorem, find the equivalent circuit to the left of this. So always to the left of the, well, it depends if RL on the right, then the equivalent Thevenin has to be to the right. Okay, so again, we need to find VTH, we need to find, so we need VTH, and RTH, and we put RL, which is 1 ohm, and then we find I. So what's missing here? VTH and RTH. So in order to do that, we have to remove the 1 ohm resistor. Okay, and then find VTH and find RTH. Let's find VTH first. And this is the two terminals, AB. VTH now, again, 1 ohm resistance being removed. So this is 4 ohm. This is 6 ohm. This is 6 ohm here, and 6 ohm, 12 and 2. Now, again, we could use the nodal analysis. Now, using the mesh analysis will be a little bit difficult because we have the current source in the middle between two meshes. So we have to use a super mesh. But Thevenin, we could use again nodal analysis, or we could use the source transformation. Okay, so let's use both. Okay, just for exercise, because this is the beauty of the circuit here, that you could use many techniques to solve for the same question, same circuit. Okay, so let's use the nodal analysis. So let's assume current here I1, here is I2. Okay, and here is I3, even though that I3 is same as I2. So VTH is equal to 4I3 or I2. Okay, because I2 and I3, because this is open, no current will flow beyond this point here, this node. So according to the rules of the node analysis, we have I1 coming in, we have the 2 amps coming into the node. Here's a node, apply KCL at this node. If we call it node A, for example, uppercase A, so I1 plus 2 is equal to I2. Okay, now apply Ohm's law. So I1 goes from the 12 to VA over, this is VTH here, okay. 12 minus VA over 6 plus 2 equal to VA minus VTH over 6. Okay, multiply by 6, we have 12 minus VA plus 12 equal to VA minus VTH. Okay, this one, so VA, take it to the other side, it will be 2 VA minus VTH equal to 24. Okay, so this is equation number 1 at node A, and then we apply the KCL at this node, if we call it B. So in this node, we have I2 equals to I3. Okay, current goes into the node, is this equal to the current leaving the node. So I3 is leaving, I2 is entering. So I2 will be VA minus VTH over 6 equal to VTH. So I0 is voltage VTH minus 0 equal to divide by 4. Okay, multiply by 12. So we have 2 VA minus 2 VTH equal to 3 VTH. Okay, again, multiply everything by 12. So 12 divided by 6 is 2. 2 VA minus 2 VH. 12 divided by 4 is 3. So this will be 2 VA equals to 5 VTH. Okay. Now we need to plug for VA. Okay, so we can replace 2 VAs equal 5 VTH. So we can plug this value here to get the VTH. So 2 VA is equal to 5. So this is 2 VA. So 2 VA will equal to 5 VTH minus VTH equal to 24. So we plug equation 2 in equation 1 to solve for VTH. So we have 4 VTH is equal to 24. So VTH is equal to 24 over 4, 6 volt, which is the same as the book answer. Okay, so this is one way, one method. We could use the source transformation to find VTH if we want, then we should get the same answer. Okay, so I'm going to erase all this here. So let's try the source transformation. Okay, so we need, again, that's after we remove the source, draw the circuit after removing the 1 ohm resistor, and then use the source transformation to find VTH. Okay, this is a 4, this is 6 here. Okay, so we could transfer, so we could have like one loop. Okay, we could have current source, convert this to a current source. And then we have the existing current source, which is 2A. Okay, this is VTH. I'm just keeping a track of the VTH here. I don't want to combine with the 6 here. And then this 12 and this is 6. So the current source value will be 12 over 6 equal 2 amps. And then this will be 6. Now we have 2 amps. 2 amps here, they are pushing in the same direction. So we could combine the 2 current sources into 4 amps. And then we have the 6 here, and then we have these 2 here. They are even series. I don't want to combine them on the circuit. I could just combine them when I find the current, when use the current division. So this is VTH here. This is 4, and this is 6, and this is 6. So now I need to find they were called I1. So I1 would be 4 multiplied by 6, the opposite resistor, divided by the sum of the resistors, which is 10 plus 6, which is 16. Okay, so this is I1. So 4 is 4, so it will be 3 over 2 amps. Then we need to find VTH. So VTH would be 3 over 2, the current multiplied by the resistance 4, which is the resistance that volts VTH across. Okay, so that will be 6 volt. Again, same result as the previous one. Okay, now RTH is very simple. So let's do it. So remove, keep it open, remove and short to terminal. RTH, this is AB, 6 here, 6 here, and 4 here. Okay, so again, I remove the, so we have 2 6s. This 6 here, let's just turn it around. And this is a short, this is open. Okay, open, short. Don't forget. Voltage source, short. Current source, open. Okay, and then 6 and 6 are in series, so it will be 12 and 4 in parallel. So RTH will be 12 multiplied by 4 over 16, the product over the sum. This is the rules if we have two resistors in parallel, only two resistors. You apply the rules of the product over the sum. If not, if more than two, then you have to use the reciprocal formula, 1 over RTH equal 1 over R1 plus 1 over R2 plus 1. Yet you could use the reciprocal also to find the equivalent resistance when you have only two resistors. But again, this will be faster and simpler. So 4, 3, so 3 divided by, sorry, this is 4, so this will be 3 ohms. Again, which is the same as. Now, to find I, simply we draw the equivalent circuit, Thevenin equivalent circuit, and we add to it the 1 ohm resistor, the one that we already removed. So remove, find the equivalent circuit, put the R load back. This is steps of solving the problem using the Thevenin equivalent technique. Remove the load, find VTH, RTH, draw the new circuit, VTH in series with RTH, then reconnect the R load. So that's what we do now after we determine VTH, which is 6 volt, RTH in series with it, 3 ohm, reconnect the 1 ohm resistor that we removed earlier, and then find I. So now you could see how easy to find I if we use the Thevenin technique. Compare that if we don't use the Thevenin, we need to use KCL here, including the 1 ohm resistor, and solve the two equations. So I would be 6 over 4 would be 1.5 amps. If we need to find the voltage across the 1 ohm resistor, will be 1 times I will be 1.5 volt. Okay, so let's move on. Okay, now Northern theorem is very similar to, the Thevenin use a lot, Thevenin is very, but again, if you have Thevenin, if you are given Thevenin, you will be able to find the Norton. So IN will be VTH over RTH. So basically, if you find VTH, you will be able to find I Northern, and then IN is the same as RTH because they are equal to they are equivalent. Okay, IN is equal VTH over RTH. So, okay, the last section here in this chapter is the how to find the maximum power transfer. In many applications, a circuit is designed to power a load. Among those applications, there are many cases where we wish to maximize the power transfer to the load. Unlike an ideal source, internal resistance will restrict the conditions where maximum power is transferred. Now, why do we need to maximize the power transfer? Because this is the optimal design, is to able to transfer as many power from the source to the load. Otherwise, then many or a lot of power will be consumed as losses, consumed through the internal resistance of the voltage or the current source. Because ideally, in practice, there is no such ideal source. Always the a resistance inside the source, such as the battery. The battery has a resistance inside it. Okay, so basically what we need to do, we are not going to do many new things concerning the equations or concerning how to solve the circuit, how to find RTH, VTH. We will follow the same steps as in the previous sections, how to find VTH, RTH. So in order to find the maximum power transfer, we need to do finding VTH and finding RTH. And then in order to transfer the maximum power from the voltage source to the load, we must match the load resistance and the R Thevenin. So in your design, for example, if you want to design a circuit, that circuit will draw the maximum power from the power supply to your load. So you must design your load resistance has to match the R Thevenin value. So if you know R Thevenin, then you could design your load to exactly match the R Thevenin in order to make your design efficient, the best that will draw the maximum power from the power supply. So to find the P max, again, as we know, to find the power formula, we know the power formula is equal to V squared over R. So in this case, it's V across the load. I mean, when we need to find the power here, we mean the power across the RL here, because this is our load. And some of the power will be lost through the RTH. We have no choice. So what is the V here? V load divided by R load. So in order to find VL, we have to find I and then find VL. So VL or I, start with the I first. I mean, I'm trying to prove this and show you how to get this formula, okay, mathematically. Okay. So first thing, we need to find I. So I is equal VTH over Ohm's law divided by RTH plus RL. That's I. Now, we could also use the I square or I square, we'll call it I or IL, multiplied by RL. So either way, we do use these two equations to find P. So since we already have I, let's use I squared times 2. So P equal I squared, I will be VTH over RTH plus RL squared multiplied by RL, which is the same as this equation. So this is how we get this equation. Now, if we have RL is equivalent to RTH, then we will find the power at the maximum power transfer. So now RL, if we make it equivalent to RTH, so then we will have, in this case, we call it P max. So at RL equal to RTH, we plug for RL as an RTH here. So we'll have VTH over RTH plus RTH. Okay, then this will be squared multiplied by RTH. This is at a condition where when RL is the same as RTH. So this will be VTH squared divided by 4 RTH squared. Because RTH plus RTH is 2 RTH, we squared becomes 4 squared, becomes 2 squared, which is 4, and RTH squared. and then multiply by RTH. So one of the RTH will cancel out, so we'll figure out it will become VTH square over 4 RTH, which will be shown. Not sure if it's been shown. Actually, was not shown in the notes here, but again, that's what is it. So let's write it down here. So P max when RTH is the same as R load is VTH square over 4 RTH. Okay, so this is the formula that we will use to determine what is the maximum power that will be transferred to the load from the voltage or from the sources. Could be more one source, I mean, depends on. And as you notice here in this graph, that when R load is the same as TH, then the maximum power will be drawn. And any other value of R load won't give us the maximum power. So the power will be drawn will be less. Okay, even with a small value of RL. So the large value or the small value of RL, it doesn't matter. It doesn't mean that it will give you the maximum power. Okay, let's do example 814. Find the value of RL for the maximum power transfer in the circuit. So basically, and then find the maximum power. So we need to find RL and P max. So the answer of this one is RTH. The answer of P max is VTH squared over 4 RTH. So if we need to find P max, we have to find RTH. Then if we find RTH, then we'll be able to find RL. And then we can find P max after we find VTH. So basically, this section is depending on the previous section of Thevenin equivalent. So basically, we need to redo the Thevenin techniques to find RTH and VTH. So basically, to find VTH, we have to remove RL, regardless what we need to find, either finding RTH, we have to remove RL, or when we find VTH, we have to remove RL. So let's find VTH first. Okay. Okay, we already removed. Again, remember that VTH is here, is the same as VTH here. Why? Because this is an open circuit. No current to flow here, 0 amps. So that means that 2 ohm resistor has no effect on finding VTH. We have to include it when we determine RTH. So this is 12, this is 6, 3, 12, and 2, and 2. Again, whatever technique we use, node analysis, mesh analysis, source transformation. So it looks like the mesh analysis is much easier. So this is I1, and this is I2. So we could say, I'm going to, sorry. So I'm going to erase only this one here to have more space. Let me move to the, yeah, just, okay. So here's the circuit actually. just since we use the book circuit here. Okay, so I1, so we write down the equation. So minus 12 plus 18 I1 minus 12 I2 equal to 0. That's equation number 1. Just reorganize. So it will be 18 I1 minus 12 I2 equal to 12. If we divide by 2, so or by 4, it will be 2 I1 minus 3 I2 equal to 3. And then from second equation or loop 2, we have I2 is equal to minus 2 amps. I think we had a similar circuit previously. Okay, and then if we need, so we need to find sorry. Okay, so we need to find I2, I1 first. So I1 would be plugging for I2, so it would be 2I1 minus 3 minus 2 equal to 3, and that one leads to 2I1 plus 6 equal to 3. So 2I1 equal to minus 3, so I1 equals to minus 3 over 2 amps, which is the same answer as in here. Okay, good. So we're done with finding I2, I1, now finding I2. I2 is given. So let me erase everything here. So write down I1 is equal to minus 3 over 2, and I2 is equal to minus 2. Now, this is VTH here. So if we write the loop here, so we have this is a plus minus. Maybe the best way to determine the VTH. Okay, so let's find again VTH across the 2 amp current source. Let's use this loop again, and let's call this voltage as V1. So V1 is equal to I1 minus I2 multiplied by 12. Okay, so 12 I1 is minus 2 over 3 minus I2 is a minus 2. So it will be 12 minus 2 over 3 plus 2. So that one will be 2 minus 2 third will be 6 minus 2 over 3 will be 4 over 3. So it will be 12 multiplied by 4 over 3 will be 16 volt. Okay, so V1 would be 16 volt, and V1 is plus minus here. So if we use the loop 2 to find VTH, so it would be minus V1 plus 3I2 plus VTH. And I'm using this loop here. So this is the voltage VTH. So VTH that's equal to 0. So VTH will be equal to V1 minus 3I2. So V1 is 16 and 3I2 is minus 2. So it will be 16 plus 6 is equal to 22 volt, which is same as, so now the book uses this loop here. Okay, and I'll show you what the book uses here. Okay, so the book uses this loop here. It will be minus 12 plus 6I1 plus 3I2 plus 2 times 0 because no current flow here. So there's I2 here, yes, there's I1 here, but there's no current here, and then plus VTH equal to 0, which is this formula. Okay, whatever you use, either this loop or the big loop, that's fine. Now, finding VTH, RTH, sorry, remove, open, remove, short. Redraw the circuit, which is this one here. Again, the 6 ohm could be replaced here if you want. So these two now are in parallel. So 6 in parallel with the 12 plus 3 plus 2. So always start from the far end opposite. Okay. So RTH would be 5 plus 6 in parallel with the okay. So let's do that. So 6 times 12 over 18. So it would be 4. So 4 plus 5 would be 9 ohms. Okay, so it's now at maximum power, as we said, RL is equal to RThevenin. So this is the answer of question number 1. The answer of question number 2, just basically apply on the value on the formula of the Pmax. So Pmax equal VTH square over V for RL, or actually for RTH, because both they are equal. And you get this answer. Okay, and again, you could use the same thing here, but what we need to do is to find, determine the RL, so that means RL, RTH, and calculate the maximum power, P max equal VTH square over 4RL or RTH. So basically, we need to find RTH, VTH. Okay, to find RL or RTH, so this is short, this is open, this is open. So we have remove RL, we have 6, 4, and 2. So basically RTH is equal to 6 and 4 is 10, and 2 is 12. So simple if you know what to do. Short, open, open. Okay, VTH might take a little bit longer, depends on what technique you use. Okay, so we remove this one here. And draw the circuit. Okay, and then we have the I think the best technique here is to use the source transformation. So we convert this into a voltage and the resistance, and we convert this to voltage and the resistance in series. Okay, so to do that, so let's put plus minus again. The head is a plus, the tail is a negative. We have 4, we have 2, so 4 times 2 is 8, and then the 2. Now we do the same thing here between this point and this point. We do a resistor and the voltage source. So let's put the voltage source first, plus here, minus here, because it's plus the arrow on the right, the head I mean. And then a resistor in series, and then the voltage source of the 20 and VTH. So again, this is an open circuit, so let's put here 6 here, and the voltage source will be 2 times 6 is 12. We have 4 here, 4 here. So if we apply KVL around this loop, now again, no current flow, so the only thing will be applying KVL minus 8 plus, again, I here is 0, so 4 plus 6 is 10, 10 times 0 is 0, minus 12, minus 20 equal plus VTH equals to 0. Okay, so basically we have minus, all of them minus minuses. So we have 30 volt. Okay, we have, yeah, sorry, we have 40. This is 0 again. So we have VTH equal 40 volt. Now RTH, which is the main thing here, probably is to, again, this is, we already had this one, sorry. So it's a 12 here. Now P max will be VTH 40 squared over 4 multiplied by 12. Hope we get 33.33 watts. Okay, so that's the solution for the practice problem 814, and that's it for. So the last thing here is the realistic sources. The Thevenin and Norton equivalent circuit are useful in understanding the behavior of realistic sources. Ideal voltage sources have no internal resistance. Ideal current sources have infinite internal resistance. The Thevenin and Norton circuits introduce deviations from these ideals. Okay, so that's the end, and there are more practice problem. Okay, so that's the end of this chapter, and thank you for watching.